everyone. In the previous class, we discussed about Hook and Brown failure criterion, and we saw that this failure criterion, which is an empirical criterion, is applicable in case of intact rocks as well as for the rock masses. The only change which differentiate between the failure criterion applicable to intact rock and the rock mass with reference to Hook and Brown criterion is their parameters. In case of the intact rocks, it is the parameters corresponding to the intact rock, while in case of the rock mass, you will have the respective parameters. And you have also seen that the parameters of the rock mass, they can be correlated with the parameters of the intact rock, especially the parameter m. So, today we will learn few aspects related to parameters of the failure criteria, and these failure criteria will include Moore Coulomb failure criterion and Hook and Brown failure criterion. You have seen that there are some difficulties which are associated with the determination of Moore Coulomb parameters under effective stress conditions. And we left the discussion with a question mark there, that how to determine these effective strength parameters. So, today we are going to have the answer to that question. Let us see how. The derivation of Hook and Brown parameters for rock mass from the intact rock, it is pretty straightforward. For intact rock, the parameters are Mi and sigma Ci, while the other two parameters, which were S and A, they can be assigned a value of S is equal to 1 and A equal to 0.5 for intact rock. In fact, why this S is equal to 1 in case of the intact rocks, that also we have seen, in fact we proved it. For the rock mass, the parameters are mm, sigma Cm, S and A. So, we have in all 4 parameters here. Keep in mind that the subscript m here for these two constants, these two parameters, this corresponds to the rock mass, while in this case for intact rock you have seen that we are using the subscript I. Now, these two set of parameters, they are related by GSI, that is geological strength index, and a disturbance factor D that reflect the quality of the rock mass and the degree of disturbance it has undergone during excavation, blasting and so on. So, today towards the end of this lecture, we will also learn about the values related to this D, that how this can be assigned. Now, coming to the Moore Coulomb failure criterion, we have seen that it is quite popular among we geotechnical engineers, and in case of the soils it is quite widely used, and therefore, we have this tendency to apply this to the rocks too. And when we were discussing this failure criterion in detail, we have seen that what is the modification that we need to make in the Moore Coulomb criterion so that it can be applicable in case of the rocks. Do you remember the tension cutoff? The main difficulty which was there with respect to Moore Coulomb failure criterion was to derive its shear strength parameters under effective stress condition for the rock mass, which we were representing as C prime and phi prime. It is really not practical to test a representative rock mass in a triaxial cell. It can only be carried out through a simulation exercise. So, when I say simulation exercise means we have to conduct some kind of numerical kind of an experiment in order to have the representation of the same condition as it would have been if we would have been able to test the rock mass in a triaxial cell. So, Hook and Brown in 1977, they simulated a series of triaxial test data for the rock masses with different GSI, MI and sigma Ci values. What does this mean? This is the intact rock parameter M, sigma Ci is the UCS of the intact rock, and when they simulated this, they took the confining pressure range between 0 and half of this UCS value, which is this. So, more Coulomb envelopes, they were drawn with these simulated data from which these two parameters C and phi for the rock masses were determined. So, you see that there is a difference between conducting the triaxial test data and the data which we have got from the simulation. So, in this case they did not conduct the triaxial tests, but they simulated these results. Now, the result of that simulation can be seen here in these two figures. You can see here on the first figure, this scale is giving us GSI, and this is increasing in this direction, that is 10, 20, 30, 40, 50, 60, 70, 80 and 90. And on y axis you have this term C prime divided by sigma Ci, which is on the log scale starting from 0.01, this is 0.1 and so on, this is here 0.2 which has been shown. Then you can see some series of these curves. These correspond to the curve related to various values of Mi. For example, this first dotted line corresponds to Mi equal to 5. The next one is for 7, then for 10, 13, 16 and so on, it goes up to 35. So, how to make use of this? You know what is the GSI for that rock mass. Then from the intact rock property, you know what is this parameter M for that rock. So, for example, let us say that you have GSI as say 40 and say Mi is 5. Now, how can I find out C prime divided by sigma Ci? Take a look here, this is 40. So, I will draw a line from here and it is intersecting this curve which is corresponding to Mi equal to 5 here. Then I join a horizontal line from this particular point in this fashion and see this is 0.01, this is 0.02. So, this will be corresponding to 0.03. So, what I am going to get from here is C prime divided by sigma Ci is going to be 0.03. So, from here I can evaluate C prime equal to 0.03 multiplied by sigma Ci. This value of sigma Ci corresponds to UCS of the intact rock, and that can be obtained with quite a precision in the lab. So, this is how the parameter C prime for the rock mass under effective stress condition can be determined. Now take a look at this figure. Again here on this scale we have GSI and it is increasing in this direction, 10, 20, 30, 40 and so on up to 90. Then on this y axis we have the friction angle phi prime in degrees, which is increasing in this direction, starting from 10, 15, 20 and it goes up to 55. Then here you can see the series of these curves are there. These correspond to various values of mi. It is varying from mi equal to 5 to mi equal to 35. So in this case, how can we obtain the friction angle phi? So let us say I take the same example, that is we had GSI equal to 40 and mi equal to 5. So let us take the vertical line from GSI equal to 40. So let us follow this, and this is the plot corresponding to mi equal to 5. It is intersecting it here. So I will just draw a horizontal line from this point, and more or less you can see that it intersects is here. So here this is corresponding to say approximately 22.5 degrees. So for a rock mass for which GSI is equal to 40 and the corresponding value of mi parameter is 5, you can have C prime is equal to 0.03 times sigma Ci and you can have phi prime equal to 22.5 degree. So this is how from the geological strength index value and from the parameter of the Hoeken-Brown criterion for intact rock, which is mi, we can determine the values for C prime and phi prime, which are the Mohr Coulomb parameters for the rock mass under effective stress conditions, which are not possible to determine from the conduct of triaxial tests. So synthetic data were generated, as I mentioned to you, to follow the parabolic failure envelope in sigma 1 prime and sigma 3 prime space, and then linear Mohr Coulomb envelope fitted to these data. This will vary depending upon the stress range which was covered. So in this case the stress range which was covered was given by this, that is sigma 3f was in between the tensile strength of the rock mass and a stress which is sigma 3 max. This Mohr Coulomb parameters C and phi, they vary depending upon the range of values selected for sigma 3f. We will see how. So using these things, Hooke gave these two expressions and these were obtained using the curve fitting exercise, and likewise here you can see this is the expression for sine of phi prime and this is the expression for C prime by sigma Ci. Here you can see that you have a term sigma 3n prime. In these expressions everywhere you have this sigma 3n prime. So this sigma 3n prime is defined as sigma 3 max prime divided by sigma Ci. So the next question which comes is that how to determine this sigma 3 prime max. This is the upper limit of sigma 3f prime and it is selected depending upon the project and stress levels. So, as a general guideline for tunnels and underground excavation, we use this expression where this sigma 3 max prime divided by sigma Cm prime is equal to these two empirical numbers are there, and then you have this term which is sigma Cm prime by gamma h. This h here is the depth below the surface, that means depth of the overburden for this tunnels or underground excavations, and gamma be the unit weight of the rock mass. Sigma Cm prime as per the Hook and Brown 1997 is defined as the global rock mass strength, which can be determined from Mohr Coulomb failure envelope fitted to the simulated data. So, this sigma Cm prime gives us the better representation of average UCS of the rock mass. This sigma Cm prime is simply the UCS which is determined from Mohr Coulomb criterion just by fitting to the simulated data, and it is generally larger than the rock mass strength that you obtain from this expression. How we get this expression? This we have seen in the last class. Rock mass strength is given by the intact rock UCS multiplied by the parameters of the Hook and Brown criterion in this manner, which is S to the power A. In case of slopes, this expression is used. So, you can see that the empirical constants here they have changed. H be the height of the slope, and again gamma is the unit weight of the rock mass. One needs to keep in mind that when you apply this expression in case of the slope, the assumption which is involved is this, that is 2D failure surfaces in the form of circular arcs, and one needs to use Bishop's method of slices. Now, from the Mohr Coulomb envelope, you will get this expression which is sigma Cm prime is equal to 2 C prime cos of phi prime 1 minus sin of phi prime. This we have seen earlier. Now, in the normal stress range of tensile strength to 0.25 times the UCS, you will have an expression like this which will give you the value of sigma Cm prime, and you can see that this is a function of sigma Ci, which is the UCS of the intact rock, plus the parameters of the rock mass, Hook and Brown parameters of the rock mass. See here, instead of mm, mb is written, but this is also for the rock mass. Now, let us have some discussion about the deformation modulus. I have already defined to you that what do we mean by this. Usually in the case of rock mass, we talk in terms of deformation modulus and not in terms of the elastic modulus. Now, this deformation modulus can be estimated from index Q using this expression, which was given by these two authors in 1993. So, this expression gives you that deformation modulus is equal to 25 times log of Q, and the condition on the Q was that Q should be greater than 1. The next one was given by Biniawski in 1978, that is deformation modulus in gigapascal is equal to 2 RMR minus 100, and this is applicable when you have RMR greater than 55. Then this expression you are aware of, that is ED in gigapascal is equal to 10 to the power RMR minus 10 upon 40. This we have discussed earlier as well. Then there are few other correlations which are available. So as per Hook et al. In 2002, this deformation modulus for the rock mass having sigma Ci less than 100 MPa is given by this expression, and in case sigma Ci is more than 100 MPa, it is given by the second expression, where you can see that it is 10 to the power GSI minus 10 upon 40, and this whole thing is multiplied by a factor 1 minus d upon 2. Then in their further analysis, these two authors modified or proposed a new correlation where they had some different form with respect to D and GSI. Take a look here that ED was given by 100 times 1 minus D upon 2, 1 plus e to the power 75 plus 25D minus GSI, and this whole bracket divided by 11. In other way, you can also use this expression in case if you have the elastic modulus in case of the intact rock, which is given as EI here. So you can use either this expression or this expression in order to get the deformation modulus as per these authors. The question here comes, how to determine this parameter D, which is the disturbance factor, because how to know this GSI, you have seen it when we were discussing about various classification systems for the rock mass. So take a look here. The first column gives you the picture of the rock mass, that is related to its appearance. The second one describes the rock mass, and the third one gives you the value of D. So here, as the picture looks like, this corresponds to excellent quality controlled blasting or excavation by tunnel boring machine. This in short we call as TBM as well. This results in the minimum disturbance to the confining rock mass surrounding a tunnel. So if this is the tunnel, whatever is the surrounding rock mass, it is least disturbed because of the process of excavation, and therefore the suggested value of D is taken to be equal to 0, that is D is equal to 0 in this case. Come to the second category, where the rock mass will have the appearance like this, and it is described as the mechanical or hand excavation in poor quality rock masses, and there is no blasting. So you see that either it is the mechanical or hand excavation, and it is in the poor quality rock masses. This also results in the minimum disturbance to the surrounding rock mass. But in case if you have the squeezing problems, these result in significant floor heave, and disturbance can be severe unless a temporary invert, which is shown here in the figure, is placed. So you see here that see if this is the tunnel, the bottommost portion point is called as invert, and this one is called as crown. So, here you can see that the temporary invert has been placed here. So, in this case you will have the suggested values of D, maybe D equal to 0 or D equal to 0.5, and no invert case you will have D equal to 0.5. Then the third appearance of the rock mass looks like this, where you have very poor quality blasting in a hard rock and very poor quality blasting. So, what will happen? On one hand it is the hard rock, and on second hand you are having very poor quality of blasting. So, the disturbance is going to be severe in this case, and that is what has been given as a part of the description here, that in this case tunnel results in severe local damage extending 2 or 3 meter in the surrounding rock mass, and in that case obviously you will have larger value of this disturbance factor, which is given by this D is equal to 0.8. Then the fourth category looks like this, where you have the small scale blasting in civil engineering slopes results in modest rock mass damage, particularly if the controlled blasting is used, as it has been shown here in this figure. However, the stress relief results in some disturbance. So, accordingly, in case if you have the good quality blasting, then you will have D is equal to 0.7, and in case of the poor blasting D will become even higher, which is 1.0. The last category looks like this, where you have very large open pit mine slopes which suffer significant disturbance due to heavy production blasting and also due to stress relief from the overburden removal. Now, in case of some softer rocks, excavation can be carried out by ripping and dozing, and the degree of damage to these slopes is less in that case. So, in case if you have the production blasting, this D is as high as 1, and in case you have mechanical excavation, this value of D is 0.7. So, from this information you can obtain the value of D, substitute it in the appropriate expression in order to get the deformation modulus, and earlier also we have seen the use of this D in various expressions. So, depending upon what is the situation at the site, what is the type of the structure, what is the type of the blasting that is being adopted at the site, accordingly the value of this D can be assigned for further use in various expression as has been discussed with you. So, in today's class we discussed about some aspects related to the parameters of Moore Coulomb failure criterion and Hook and Brown criterion, and we could see that from the parameters of the Hook and Brown criterion one can obtain the Moore Coulomb failure criterion parameters for the rock mass under effective stress conditions. Then we saw some aspects related to deformation modulus along with the discussion on how to assign an appropriate value to this disturbance factor D. this was all about that I wanted to discuss with respect to the intact rock and rock masses and the empirical criteria, that is Hook and Brown criterion. In the next class, we will learn about few other failure criterion which are applicable in case of the rock mass. One is the single plane of weakness theory, and the second one is the shear strength of the joint walls. Thank you very much.